Zoom in the meeting to please not talk anymore for a while here until there's questions, because our sound in the room picks up everything. So anything that you say, if you're sitting in the room here, to the friend next to you, anything that you say might go to our entire Zoom audience. Welcome to the November meeting. It's kind of hard for me to say November. It's hard for me to realize that it's actually November now. But welcome to the November meeting of the Tucson Amateur Astronomy Association. We're here every first Friday of the month, and we're on Zoom tonight, and we're on Facebook, and then we have people in person in the meeting. So we appreciate all of your coming. I'm Mae Smith, president of Tucson Amateur Astronomy Association, and helping us tonight with technology, we have Jim Knoll and Terry Lappin, and Susan Knoll is operating our camera for us. So we have 3 people involved in the technology, but we still were a minute or 2 late getting the connections done, because sometimes our making connections here at the U of A is a little bit of a slow process, and sometimes before we get the meeting started, it gets started and it drops off and we have to start again. So, but we appreciate the diligent work here that we have. Tonight, we have a wonderful guest speaker who's going to share some information about the moon, some special information about some things that are going to be happening. And this is Dr. Angela Marusiak, and she's on the faculty here at the U of A in the Lunar and Planetary Lab. And so, Angela, I will turn it over to you.
Can you hear me now? Feel like the old spring commercials. Yeah, thank you for joining me here tonight. So let me go ahead and share my screen so you can all see what I'm talking about. So for tonight, I'm going to be talking about how we can explore our moon through seismology, which is a geophysical technique that has been really, really important here on Earth, and has actually been part of the Apollo legacy from the beginning. So out of curiosity, though, who here is familiar with the Apollo programs? Okay. You never know. Trickier question. Who here is familiar with the Artemis programs? Okay, so still quite a bit. Good to see an astronomy club. But yeah, Artemis is really exciting. I'll be talking about it later tonight. And here at the U of A, we have the unique opportunity to be a part of it. So I recognize that this is an astronomy club. So I figure it might be helpful if I start with a little bit of some backgrounds on seismology, in case maybe you may or may not have covered it in your earth science class. I know it's not typically taught everywhere. So I'll go over some seismology basics just so we're all on the same page as I like talk about some of our findings and expectations. And I'll also go over what Apollo's legacy was, why it was so important, not just for, the space race, but for science, and what we hope to do with Artemis. So why are we going back 50 years later? And then I'm going to wrap up by bringing it really close to home and talking about what we're doing over at U of A and just across the road at the Kuiper building. So seismology has been sort of studied since almost the dawn of time, really, especially as humans were in areas where there were earthquakes that were common. We sought to understand why they were occurring. It wasn't really until the 1st century BCE that we started to develop tools to start to study them from a science level and not just necessarily like a mythical sort of type. So what's pictured here is a replica of what's called a seismoscope. So it was developed by the Han Dynasty, And how it worked was the little balls that would be in a dragon's mouth would drop down into a frog's mouth if there was an earthquake. And depending on which ball dropped, it would tell you roughly the direction that the earthquake was coming from. So it couldn't tell you magnitude, it couldn't tell you how bad it was, how far away it was. It just basically told you, yeah, there was some shaking in that direction. But it was really important because for the emperor at the time and for the government, they could go and send aid and go and investigate, or people could go and like check in on their neighbors, that sort of thing. Then it really wasn't until the 19th century that we really started doing how we think of seismometers today. And this is because of the Lisbon earthquake. So what happened is there was an earthquake off the coast of Lisbon, Portugal. This was particularly bad for two reasons. A, earthquakes shake the ground, which is bad. But it also happened offshore, which meant there was a tsunami. Another common effect of an earthquake is that there tends to be devastating fires afterwards. So the city of Lisbon, which at the time was a very important port city, was almost completely leveled. And this was at a time, sort of during the Enlightenment, where we started to really go into sort of modern science. So from this, people wanted to understand, how are earthquakes happening? When do they occur? Why are they occurring? Can we predict them? Can we prevent them? What are things that we can do? So this really was sort of the advent of seismology as a science as we know it today. So from this earthquake, people started to develop instruments so that we could measure ground motion and measure earthquakes. And then in the early 1900s, we started to look at seismology not just as a way of looking at earthquakes and hazards, but actually noticing these waves, have patterns to them. Can we use wave theory to actually understand things about the Earth beyond just a hazards point of view? So one of the things that we talk a lot about in seismology is seismicity. So I'd be a terrible seismologist if during a lecture I didn't ask who here has felt an earthquake. I'm sure most people, yeah, God, you can raise your hands. Out of curiosity, keep your hands up if you were not in California when it happened. Okay, because normally when I say that, most of the hands go down. Makes sense. California is one of our more seismically active states. So what I have mapped up here is from the USGS. It's actually a really neat tool if you like seismology. So what I plotted up is all the earthquakes that happened in the year 2023, so our last complete calendar year, that were above magnitude 4.0. What you'll notice is that the earthquakes tend to form a pattern. You might be able to see there are some red lines here. Those are the plate boundaries. They're actually kind of hard to see because they're covered in earthquakes. And that's because most of Earth's seismicity is driven by plate tectonics. Seismology was really, really, really important to the discovery of plate tectonics, which most people don't recognize or realize. Plate tectonics is fairly new in terms of like science theories. It really wasn't developed until like the 50s or 60s. In fact, many of the people that developed the theory are still alive today. And earthquakes was one of the key pieces of evidence for it. That's because if you'll notice, not only are the earthquakes occurring along those plate boundaries, if you look at the size of those circles, those correspond to how big the events are. And what you'll notice is that a lot of the big events tend to be in the Andes, where you have a subduction zone, or along the Pacific Ring of Fire. And then you'll notice along like the Mid-Atlantic Ridge here, they're not as big. And in California, same thing, they're not quite as large. And this is because the seismicity, so the where, when, and why, is being driven by how these plates are moving. So you have bigger events when you have plates sliding together. You have relatively smaller events if they're sliding next to one another or spreading apart. So in addition to sort of the naturally occurring large events, we also have induced seismicity. So this is same calendar year. This is down to a magnitude 2.5. So what you'll notice is, again, California is basically covered in earthquakes because of the San Andreas Fault, not surprising. What you might find slightly surprising is Texas and Oklahoma, especially Oklahoma, right, have quite a large number of earthquakes. That is because of the wastewater injection. So a lot of times we talk about fracking and induced seismicity. So the fracking itself is not necessarily creating large amounts of earthquakes. It's the pumping down of the water that ends up generating a lot of induced seismicity. So there was quite a while when Oklahoma was actually one of the most seismically active states in the US. And even though these events were small, every so often you would get a larger event that could cause damage. Some other things you might notice is like Missouri tends to be kind of seismically active. That's the New Madrid zone near the Memphis area. Also, if you're eagle eye, you might notice that there's this event down here. So that was an event that happened back almost a year ago. It was like September of 2023, actually near Tucson. So if you were awake in the early morning, you might have felt some ground shaking from a nearby magnitude 4 event. So this just goes to show you that although most of Earth seismology is from plate tectonics, we do get seismic events, what we call interplays, so between those plate boundaries. In addition to earthquakes, we can also have explosions. So in like Montana, you'll notice some of these circles are actually diamonds. Those indicate that that's not a naturally occurring earthquake. It's from mining explosions. You can also have avalanches and rockfalls. So like when Mount St. Helens erupted, that created a very large seismic event. And then in glaciers, we can also have like ice quaking and ice cracking. And all these things are things that we study here at the U of A. I myself have looked at all 3 of those, like avalanches, rockfalls, ice quakes. So once we have those seismic events that are generating ground motion and ground shaking, we can actually look at the seismic waves to see the interior of Earth. And there's a couple of different types of seismic waves that we can look at. I should mention seismologists are not creative when we come up with names, as you'll probably see as a theme throughout this presentation. So waves that travel through the interior of a body are called body waves. Waves that travel along the surface of a body are called surface waves. Makes it very easy when you're taking seismology to remember those things. The first arriving body phase is called a primary wave or P wave. It's also a compression wave. These you tend not to necessarily feel during a seismic event. Sometimes animals, depending on their hearing range, will hear them. So sometimes like you'll see videos where like dogs suddenly like perk up right before an earthquake, and that's because they can hear the compressive sound. You also have secondary or S waves, again, really creative there. These are shear waves, so they move transverse. So if a wave is traveling forward, they're going to move sort of side to side. These can be a little bit more damaging. This is normally the first wave that you would like feel during an earthquake. And then you have surface waves, which you can have Raleigh waves. They have sort of this like a rolling backwards sort of motion to them. And then love waves. These are the ones that tend to be most damaging during an earthquake because they're traveling along the surface. They move the ground the most. So that's where you get a lot of the damage. And then there's also things called normal modes, which really only happen on Earth. It's sort of like ringing a bell. But a combination of these waves allow you to look at the interior of Earth. And this is how we know things like that we have a solid inner core, and we have a liquid outer core, and we have a really large mantle. So kind of going back a little bit, so in the early 1900s, after that Lisbon quake, we had really sparse locations. And this is sort of the early single station seismology, as we call it. And this is most analogous to what we do on other planets, because we can't go and set up a huge array of seismometers like we do now. So we can learn a lot from the techniques of people over 100 years ago and how they did science and apply them to today. So even though we had only a couple of events, maybe not the best technology at the time, we were able to do things like figure out how big is the core. One of my favorite anecdotes, the inner core was discovered by a woman, Inga Lehman, one of the few female scientists at the time back in the early 1900s. So she wrote a paper where she noted a seismic phase, and it led to the discovery of the inner core. So as a grad student, I was trying to do my due diligence and read up on all these papers because I was studying the core. So I was trying to find her paper. And now modern times, if you had a big discovery like the inner core, you'd find all these newspaper clippings and you'd probably title your paper something really catchy like "The Inner Core of Earth is Discovered" or "Discovery of the Inner Core." Her paper was called P prime, literally 2 characters, P apostrophe. So I had to do a lot of digging, and eventually after an embarrassing long time, I just went to my advisor and I was like, I cannot find this paper for the life of me. And he's like, this is what it is. And I was like, oh, okay. Would have been nice to know ahead of time, but thanks, boss. Also, a lot of the original papers are in German, which also made reading them a little bit different since I don't speak German. But what we can do with these seismic phases is essentially create like a almost MRI, X-ray, or sonogram, if you will, of what's going on. Sorry, I'm a new mom. I love showing off photos of my kid. Um, but essentially what we can do is look at how these seismic waves pass through a body and be able to figure out what's going on beneath our feet. So a lot of times this is used in the oil and gas industry to look for gas reserves, which is why seismology is really popular in Texas and in the Gulf Coast. But we can also look for things like subducting slabs. So as I mentioned earlier, we can get a lot of big earthquakes as when plates collide. When these plates collide, one can dive down deep beneath the other one, and we can actually see this through seismic waves. And we can map out how they're traveling down all the way from the surface down towards the core. We can also see what we refer to as large low shear velocity provinces, LLSVPs. These are basically geologic features that we think are responsible for hotspots, so think Yellowstone, Hawaii. But this is really what I want to illustrate why seismology is super important, because a lot of what we know in geology is tied to what we have learned from seismology, because it is one of the unique ways that we can look really deep down and see what's going on the inside of a planet while we're still at the surface. So much like how a doctor can diagnose broken bones or can look for tumors or things in your body using different sort of scans, seismology can do the same thing for a planet. So it allows us to explain a lot of things, like why does Hawaii have volcanism even though it's not near a plate boundary? Why is Iceland acting kind of weird? Yeah, things like that. So it kind of makes sense that since seismology was so critical to our own understanding of our Earth, that as we began to leave our planet and explore the solar system, we want to take those lessons learned with us, which brings us to Apollo. So Apollo launched in 1969, and with it, it brought seismometers. So Buzz Aldrin and Neil Armstrong, they installed the first interplanetary seismometers. So this is actually a photo of, I forget who it is, installing the Apollo 11 seismometer. So Apollo 12 through 17, not 13. If you don't know why, watch the Tom Hanks movie. Created a seismic network, and it was actually pretty long-lived. So I have mapped out here when they got installed relative to how long they went. And it's actually kind of, I don't know if it's sad or interesting, but the reasons they were eventually turned off was for budget reasons. So the instruments were doing well, they were recording data. It was purely monetary reasons that they were turned off and we stopped collecting data. And we did both active and passive experiments. So passive is when you sort of just sit and listen for the background. So you're looking for like naturally occurring events. Active is when you're creating those events. So things like the lunar modules lifting off the surface, detonating explosives, those are all active sources. And we were able to get a lot of really key findings from Apollo. So one of them is that the moon is actually differentiated. So it does have a core like Earth. We didn't really know that for certain before Apollo. We actually got the size of the core roughly. I say roughly. We also realized the moon, despite not having plate tectonics, actually is seismically active. And one of the more common events is something we refer to as deep moonquakes. Again, we're super creative. These are moonquakes that happen deep within the moon. So here they're plotted out. And one of the things I want to point out is the seismic stations were all on the near side and roughly near the equator. This is because, Apollo, the main goals were not, to do a seismic exploration of the moon. The main goals of Apollo is let's get people on the moon before the Russians, and let's do that in safest way possible. So while they did want to go and explore some different areas, from an engineering point of view, it's much easier to land on the near side, near the equator, than to try to go to the far side of the poles. So one of the things you might see is that these deep moonquakes happen mostly on the near side, and they don't seem to happen in this far side area. And that is a big mystery, even going on today, is why is that? Is it because all the stations are on one side and they can't see on the other side of the moon? Or is it for some reason the far side of the moon is different than the near side? Because we know the surfaces are quite different. So it's a question of, how far do those differences go if they go down to the core? Some of the other events that they were able to detect were impacts, so meteorites hitting the moon. This is actually really important because once we have the modern impact rate, we can back out what it might have been like in the past. we can also extrapolate that to other bodies. And counting craters is actually the predominant way that we age bodies in the solar system if we don't have direct samples of them. And then, yeah, as I mentioned, there are no plate tectonics, but we do still have shallow events because as the moon gets older, it cools down and it shrinks. So kind of like if you have like older fruit that's been sitting out, as it ages, it sometimes will shrink and get like wrinkly on the top, like especially like a peach. Similar things are happening on the moon. So one of the limitations, though, with Apollo is that the data was not the best quality. There's a couple of reasons. One is like it is 50-year-old technology. We've advanced a lot since then. A lot of things have. The digitization has greatly improved. So if you notice, like in the seismogram here, it looks really like blocky and jarry. That's not great. That's basically an issue with what we call like the bit rate or the bit depth. The sampling rate, so how often we're collecting data, normally you want it to be nice and even, but with Apollo, it was actually somewhat dependent on temperature. So instead of being nice and even, every so often it would speed up or you would skip a beat essentially, which is not great when you're trying to do data. Clocks were also not quite as precise as we would have loved, and had some issues. So because of that, if we compare seismograms of the moon to the Earth, the moon is not nearly as good of quality. There's also issues with the moon's surface is really, it's covered in what we call megaregolith. And essentially it's like a soil that's really rough, it's broken up, it's jagged. If you were to scoop it up in your hand, it'd be really rough and feel almost like sandpaper. And that's because the moon doesn't have wind, so it can't erode and smooth out. And essentially what that does for a seismometer is it creates this sort of like ringing noise. So instead of having these nice sharp arrivals, they end up kind of shaking and reverberating and hiding other seismic phases, which makes our jobs much difficult. Which is why we're heading back. So there's a couple of different programs going on with NASA. One of them is in the commercial sector. So there's a program called CLPS, the Commercial Lunar Payload Services. This is a program where commercial companies are building these landers to attempt to land at different spots on the moon and carry different science instruments with them. The ones that have gone so far are less than successful. The first had a hard landing. There was another that had a soft landing and then fell. So hopefully the next couple of ones will do much better. But that's also kind of the point of the program. It's that we want to give these commercial companies a chance to go try it out. If they fail, it's not huge amounts of money that was invested in it so that they can learn from their mistakes and hopefully get it right the next time. But what's kind of interesting for a seismometer is one of the instruments selected under this PRISM SALSA call is the Farside Seismic Suite. So that will be heading to Schrodinger crater, which is down near the south pole of the moon. And it's going to have a seismometer on it. So the seismometer is this little square box that will sit on the lander deck. And it's actually going to use flight spares from the InSight mission. So if anyone's familiar with that mission, it was a seismometer that was sent to Mars back in 2018. It lasted until 2022, I want to say. And it had really sensitive instruments on it that were able to do, honestly, I could do an entire different talk on InSight. But it was a really important mission because it was the first seismic mission since Apollo. But we have flight spares from it, so we're repurposing them for the moon. I have launch in 2025. It actually just got delayed till 2026. But it will be heading to the moon eventually. The other opportunity, and the one that I am really, really excited to talk about, is Artemis. So if you're familiar with Greek mythology at all, Artemis is the sister of Apollo. She's also the Greek goddess of the moon. So I think it's a very fitting name. So Artemis is essentially the more modern equivalent of the Apollo missions. Actually, Artemis 1 has already launched and was successful and completed. Artemis 2 should be scheduled for 2025. It will take a crew and orbit around the moon. So if you're familiar at all with Apollo history, it's more akin to Apollo 10. And then Artemis 3 is going to be the first time humans have set foot on the moon in over 50 years. So Currently, it's scheduled for a September 2026 launch. What's also kind of exciting is, true to the name Artemis, we're expanding the pool of who will be going to the moon. So it's no longer just, Navy test pilots. So we are going to have the first woman to set foot on the moon, and we're also going to have the first non-American to set foot on the moon, probably a Canadian. But it's really exciting because now in the modern era, it's, the moon is for everyone, and it's not just purely for military and space race purposes. But Artemis has a couple of science goals that they want to try to achieve over the different missions that they plan to send. So some of these things are understanding planetary processes. So does the moon have recent volcanism? What is the tectonic setting? How is it differentiated? So can we nail down some of those initial findings from Apollo in terms of how thick is that crust? Is there an outer core? Is there not an outer core? We want to understand the character and origin of lunar polar volatiles. So this is important for things like, is there water on the moon that we can use for more permanent habitation or for repurposes for fuel? Looking at the impact history of the Earth-Moon system. So can we better understand things like the late heavy bombardment or better constrain like asteroid risk if we understand the history of impacts? Looking at records of the ancient sun and our astronomical environment. So going beyond just Earth when we think about what's going on around us. Observing the universe. So the moon does not have an atmosphere, so it makes using telescopes much, much easier because you don't have to do atmospheric corrections. We also want to conduct experimental science in the lunar environment. So one of the instruments that will be heading with Artemis 3 is called LEAF, and it will be taking plants up, and the astronauts will be looking at, how could we potentially grow plants on the moon, which is something we would need to do if we want to create more permanent settlements outside of Earth. And then also we want to think about how do we investigate and mitigate exploration risks? Because we don't want to be sending people to the moon and not having them come back. So as a seismologist, the thing that I'm most thinking about is how seismically safe is the moon? Arizona is pretty safe. We do have the occasional earthquake, but, we don't necessarily have to have our building codes up to the same level as, say, Alaska or California. So how does the moon fall in between there? How likely is it that we can have damaging events? And the ones that I've highlighted are ones that a seismometer can help address. So we can look at things like planetary processes. We can look for signs of volcanism. We can look at the current impact rates and how that extrapolates backwards in time. And then, yeah, we can look at the seismic risks and hazards and figure out, is this something that astronauts need to be concerned about? Or is, the list of 50 other things that can kill them a little bit more pressing? So this takes me to seismology here at LPL. So back in, I think it was March or April, we found out that the Lunar Environment Monitoring Station was selected. So this was a call back in the summer. It was for the Artemis 3 deployed instruments call. I think they had over 50 applications and only like 3 were selected. So it was quite competitive. So the leader, the PI is Mehdi Benna, who is out of UMD, Baltimore County, and Goddard Space Flight Center. But U of A will be the one supplying the sensors. So the seismometers will be coming from right here. So U of A partnered with a company called Silicon Audio. They're based out of Austin, Texas. So they are building the sensors, and we basically do a lot of the science and integrate them out here. So we're hoping to, potentially use that nice new ARB building. And also some resources over at Kuiper to test out these sensors and get them ready to head to the moon. And this has been really a long time coming. So U of A has been partnered with Silicon Audio for almost a decade. I myself got involved as a graduate student back in 2018. And we have been developing seismometers for planetary applications through a variety of programs. So what I have pictured here are some of the tests that we did in Greenland and Alaska. So it's probably hard to see, but that is actually me. That's one of our other faculty members, Danny Dell'Agostina, standing next to me. We're also in that photo down there. So I do want to take a slight personal side about this photo. So this was taken 2 or 3 months after I had proposed my PhD thesis. So right before I proposed my thesis, I was at a workshop for ice seismology And everyone was talking about all the glaciers that they go to and all the cool stuff that they do. And I was like, well, I'm a planetary seismologist. I can never go to my field site. It's too far away. About a week after that, I defended my proposal where I talked about how I was going to spend the next 3 years in my nice climate-controlled lab doing all these models and running all these simulations to figure out how seismology works on icy ocean worlds. And I was going to stare at a computer. About 2 months later, my advisor comes into my lab and says, hey, we got funded through the University of Arizona in a NASA project to look at seismology on icy ocean worlds. He's like, do you want to be a part of it? I was like, yeah, absolutely, sign me up. He said, cool, you're heading to Alaska next month. And I was like, what now? So fun fact, it's really hard to find cold weather gear in Maryland in August. Yeah, so a month later, there I was standing next to Danny out on a glacier in the middle of the Alaska range, testing out seismometers to see how they perform for icy ocean worlds. Because of that partnership, it eventually led to me getting hired here. So that kind of goes to show you, you never know sort of where life is going to take you. And sometimes it's better not to ask too many questions when your boss offers you an opportunity. What's kind of interesting, just to get back to LEMS now, what makes us really unique as opposed to some other seismic deployments is we are going to be deployed by an astronaut, which makes us really unique because all the other seismometers, InSight, the Farside Seismic Suite, they're all on a lander deck. So we have the opportunity to have someone actually go with tools and put us in the ground, which for a seismometer is really important. So on Earth, we tend to bury our seismometers down quite a few feet, cover them up, protect them from bears and wildlife and that sort of thing. It's really hard to do that with a robot. Yeah, you send a human to the moon and give them a shovel and they know what to do. So we have 2 different sensors that we're going to be sending, a short period seismometer and then a broadband instrument. So our short period is much smaller. It's 3 components and its sonde is smaller than this. So it's closer actually in size to like a soda or beer can. Actually, it's closer to, yeah, the Diet Coke you have there. So we're gonna have the astronauts basically just like push it down right into the ground. Our VBB or our broadband is a bit bigger, so that they're just gonna do a trench and then kind of cover us. But that's actually a huge improvement over Apollo, because if you remember from that photo I showed earlier, the Apollo instruments, they just kind of basically put it down on the surface and then like threw a thermal blanket over it and called it a day. So that's one of the reasons we hope to have much better data than Apollo. So some of our science goals are going to be to characterize the moon seismicity. So now that we are much more sensitive than the Apollo instruments, we hope that we can get a better record of what the moon is actually doing. Because of our location near the South Pole, we can address that question of, do we have those deep moonquakes on the far side? So were they just kind of hiding from view, or do they actually not occur, which would be a really interesting science question. So we want to look at things like the internal structure at the South Pole. So like, how thick is that crust? Is it much different than the near side? Is the core structure different? If it is, why? Because normally we think of planetary bodies as being somewhat homogeneous. And then for the human exploration side of things, we want to assess the local and global seismic hazards. So if we go and we decide we want to be a more permanent presence on the moon, which areas shake less than others and how much do they shake? Do we need to consider that when we build our buildings, or can we maybe have slightly laxer code because we need to focus on things like radiation or extreme temperatures that might kill us? So in terms of seismicity, there's a couple of different things we should detect. So all the nice little circles that fall above these lines are things that we can see. And this kind of also illustrates how we're much more sensitive than Apollo. So Apollo geophones are this green line, and then their short period sensor is this gray line. Ours are the red and blue, so they're well below that line, meaning that we're going to be able to see a lot more events, and we're also going to see events much more clearer than Apollo was. So we can look at things like scattered body waves. So those P and S waves I was talking about that pass through things like the core and the mantle. We can see those deep moonquakes that are occurring. We can see both artificial and natural impacts. So, meteorites hitting versus the landing systems leaving the surface. We can also see some more high frequency events. So one of the events that I didn't talk about quite yet is the thermal event. So as the moon goes through its huge temperature swings, it generates seismic events from the heating and the cooling. And then also looking at those shallow moonquakes, which are much more rare, but much more likely to actually cause damage. So as I mentioned, these are some examples of the seismicity that we can look at. And what's kind of interesting is we can kind of be detectives in order to figure out what type of events they are as they occur. So I know to most people, these just look kind of like squiggles or spikes in the data. But to a seismologist, this is like great fodder that we can go and look at. So for like a deep moonquake, we can see it has fairly high amplitudes, really long durations, like thousands of seconds, and it has lower frequency content, meaning it tends to be much like lower, longer period. In impact, has pretty decent amplitudes depending on how big it is, and it has kind of a wider range of frequencies. Shallow moonquake is somewhat similar. What's kind of unique about a shallow event is that when it first happens, you get a lot of high frequency and then it dies off through time, and you end up with just this sort of lower frequency down here. And then there's actually two types of thermal moonquakes. One are naturally occurring from like the regolith and boulders left behind, and the other is driven by material we've left in the field. So like lunar modules get left behind. And these are made out of metal. So as metal heats up and cools, it can also contract and create these thermal moonquakes. And we can actually tell the difference between the two based in part on how large they are and also whether they're relatively low frequency or higher frequency. So this can also tell us a lot about sort of like the near surface and what's going on, and might also be able to help us figure out, where could that water ice be located. And we've done some analysis, and based on how long we expect to survive on the surface, which is also partially dependent on how much money they give us. So please write your congressman and tell them to keep funding us. We expect to see anywhere from hundreds to thousands of deep moonquakes. We could see tens to hundreds of impacts. And again, depending on how long we live, we should be able to see some shallow events. They are quite rare. So if we only last for 3 months, we have a decent probability of seeing at least one or two. And one key part is there is a bit of a difference between seeing an event, saying that's an event, and being able to use that event. So really only about 10% of the events that we can detect and say, yes, that's an earthquake, will actually result in us being able to use them for science. So this is a little more technical, but just in case anyone's kind of curious how we actually do this. So when seismic waves pass through different medium, they tend to bend and reflect, and we can identify the different arrivals. So we can look at things like the initial arriving P wave or S wave, and then other different waves that reverberate. And we can back out the different layers that are beneath us. So we can see things like the regolith, the like more crustal, more solid bedrock, if you will, unfractured crust, and then eventually we can see like where the crust mantle layer is by looking at these different reverberations. We can also look at a core structure through a somewhat similar method. So when you have a deep moonquake, it'll send out seismic waves, and these will bounce off of things like a partial melt layer if it exists, or they'll just go right down to the outer core and then the inner core. So we can look for these different reflections as they show up on a seismogram and be able to back out. Not only do these layers exist, but also how far beneath the surface are they? And this was actually done both with Apollo data to get a little hand wavy core sizes. More recently, it was used on the InSight mission to Mars. So this is from one of the papers that I co-authored back when I was at JPL a few years ago, where we used seismic waves to go and identify these peaks here and use them to figure out what is the size of the Martian core. which was one of our big science objectives. So we can basically take the exact same technique and apply it with Artemis. And of course, really important to the human aspect is how do we go about like looking at seismic hazards? So we did some modeling, and we've also used some Apollo data. So what the green stars represent are potential landing sites, or excuse me, the cyan here, sorry, is the potential landing sites. The green stars are where we have known seismic activity. So you'll see that not too far away from where we might be landing, we do have quite a number of potentially large events that could occur, that have occurred in the past. And these yellow squiggles are other areas that we think could produce these large events. So we're well poised to be able to get quite a few potentially large events. And the thing to keep in mind is, the moon has 1/6 the gravity. So it doesn't take too much to really get the ground to move and shake. So on Earth, a lot of times we think about seismic hazard in terms of the number of Gs it's producing. So if you have an earthquake that's producing 1 G, you can kind of think of it as it's bouncing you up and you're almost weightless compared to the ground because of how much it's shaking. Also, I feel like I need to do my seismology duty. If you're in an earthquake, for the love of God, do not try to run. It always bothers me in disaster movies when they do that. Don't just drop cover, hold on, do not move. Most people actually get injured trying to run to safety in an earthquake. So please don't run during an earthquake. But we can, what we did is we actually simulated a shallow moonquake and how much it would shake. And it turns out it does not take much. So it might be sort of hard to read this, but sort of the typical shallow event we expect to see, we can get moderate to strong shaking, even if we're 20, 30 kilometers away. And if we're unlucky enough that it happens very close to us, like say this yellow right next to where we plan to land, it can be violent shaking. So in terms of like ground accelerations, the lighter you go, the closer to 1G, 10G, or even 100G you get. So you can see that, yeah, if you're close enough to an event, you can get pretty violent shaking. So even though these events are probably pretty rare, you actually do still want to consider them for permanent habitation. So with Artemis, the longer that we're deployed, the better chance we have to see some of these events and be able to figure out exactly how often are these occurring. So are they sort of like a once a year type of thing, or are they like once a decade? Because that will help inform us on, if we do want to make a permanent presence on the moon, where do we want to go? So some of the future work that we want to do is right now in Texas, we are putting together our instruments. So I'm getting images almost daily of our instruments slowly being built up and put together. So these are for our engineering and training models, which we're going to be delivering eventually to Johnson Space Center. So the astronauts can actually train with our instruments and learn how to install them and set them up and all those fun things. We need to environmentally test them. So essentially take them, put them in or set them up on a rack and shake the crap out of them and see if they survive, because that will simulate if they're able to survive a rocket launch up to the moon. We also have to put them down to cold temperatures to make sure they can survive at the lunar temperature ranges that we expect. So that will be happening probably later in the winter, potentially here. And then, yeah, we're going to be eventually training the astronauts. And once we pass all of our checks, build fresh instruments with all the lessons that we've learned, which hopefully will not include too many failures, and deliver those flight sensors so that in September of 2026, they can head to the moon with the astronauts. And then hopefully we'll be able to watch them getting installed at the South Pole of the moon. So with that, I'm happy to take any questions that folks might have.
In the audience. Okay, we have a hand and Jim is coming.
Hello. How is Artemis 3 going to reveal the ancient sun?
That one is not one of our particular science goals for the seismometer. I think there is another instrument that might be looking at electric fields or something. So not all of the Artemis science goals have to be achieved on each Artemis mission. So besides Artemis 3, there is going to be Artemis 4, 5, 6, potentially even more. So that's probably a science goal that will be targeted more for a later mission. That is beyond the scope of my knowledge.
Do you have a mic? Okay, super.
How long are these instruments expected to last?
So our initial goal is 3 months, but we've designed them that they could last potentially several years. So ideally, we want to keep going as long as we have funding to keep going. And we've designed our instruments so that they should hopefully survive through most of the lunar night. Depending on how the solar panels go towards the end of the mission, they might have to be like the InSight mission where they turn off for brief periods and then come back on. But yeah, at least 3 months is our like minimum.
Okay, someone else? Angela?
I'm not a scientist or anything, but I know that you said you were collaborating. It's not just about the United States. Could you tell me, are we collaborating with China
No.
or are we competing with China?
There is a current mandate where we are not allowed to work with China. That is written into congressional law.
And that's very recent or,
I want to say 2003.
okay.
I could be wrong in the exact date, but there are very specific guidelines on how US scientists can interact with China. China is not involved in the Artemis missions at all.
Any other questions in the room? Ah,
Yeah, I'm trying to figure out the mic here. Okay. You had mentioned early on that the Apollo seismometers were turned off. What would be the point of turning them off? Were they using power that
Money,
going to something else? I mean,
it's money.
no, I
it-
meant, why not leave them on? What does it
Because-
hurt to leave them on?
Because someone has to collect the data. You have to have engineers that are pulling the data down. You have to pay scientists to look at the data. That costs money.
Okay,
Yeah. No, it doesn't.
it
Yeah.
doesn't make any sense, but thank you.
Yeah, are you going to have the sensors shook and temperature cycles at the ARB or is that at NASA?
We're considering potentially doing some testing here, but a lot of it will probably happen. I think at Goddard is currently the
Okay,
plan.
thanks.
Although we've been working on developing these sensors for a long time, so some of the vibrational testing will happen local. Whether the temperature happens, it probably will not happen at the ARB because actually, if anyone has been to that building, their TVAC chamber is huge. It's actually too big for us. So if it happens on campus, it will probably happen over in Kuiper. Although it's still being finalized, so don't hold me to that.
okay, Doug?
So China had that rover on the far side. Did they have a seismometer on that? And was there any data collected that used for anything?
So I do not believe they had a seismometer on that mission. I think future ones are planning to. The JAXA, the Japanese Space Agency, did they have a seismometer? I think they had a seismometer when they attempted to land. The Indian Space Agency, which was actually one of the first ones to land at the South Pole of the Moon, they did have a geophone. So they were able to do some seismic recordings. What other countries share with us is sort of up to them. So China does not share their data very willingly. So what we may or may not get out of them is unclear. JAXA tends to be very friendly with the US. It would surprise me if we weren't allowed to eventually access that data. It's also worth noting, like there is sometimes what we call, oh gosh, I'm forgetting the term, not probation. it'll come to me in a second. Essentially, when you collect data on a mission, some things like images will become publicly available immediately. Other things will, embargo, that's the term, are embargoed for a few months. So like with the Mars data, the InSight team was allowed to look at it for approximately 6 months before it became publicly available. So something's a little similar, I don't think it's quite as long. So the Artemis team will look at the data first and then it will become publicly available to everyone so that even if you're not on the Artemis team, scientists across the US and the world can, eventually look at the data and try to do some science with it.
Okay, thank you. Any other questions in the room? Okay.
I'm wondering what countries we're friendly with and which countries can we cooperate with or have joint missions with?
Yeah. So there's the Artemis Accords. So some of the countries that we tend to work with a lot on missions, Canada for one, the ESA. So that's Germany, England, France. We work with them a lot on seismometers, actually, those 3 countries. We've worked with Poland before on the InSight mission. I believe Italy, the Japanese Space Agency we tend to work well with. I'm not honestly sure about the Indian Space Agency quite yet, how well. I believe they're more open to working with things, but I'm not 100% tied into that political situation. And it does tend to be more governments that decide that than the scientists.
Okay. Any other questions in the room? Okay. We will then go to, I guess, Facebook. Terry,
Well,
you ready
we can
for
do
Facebook?
Zoom first if you want. Yeah, let's do Zoom first. All right, so Tom O'Keefe asked, could you explain how the Alaska seismometer works? It looks like maybe 2 plates and 2 phones.
Let me go. Okay, so this is a table. Our seismic sensors are these, right, can people see my mouse? Okay, yeah, those are the seismic sensors. So those are screwed into the mock table that we had set up. So for this experiment, what we were doing is testing seismic responses if you're on a mock lander, like FSS is going to be for the moon, or if you're actually buried beneath the site, like, so how much noise does a lander actually introduce? So what we did is we made this table, I believe it's like aluminum, and we had it designed so that our instruments could screw directly into the top, which is those 2 instruments you see there. There's also instruments attached to the legs here that you can't quite see from this angle. And then we had instruments buried beneath the lander as well. So those, the ones pictured here are commercially available off the shelf from Silicon Audio. So we were mostly testing sort of the signs that you can get out of those sensors. What we've then done is ruggedize them, made them smaller, made them more robust for planetary applications for the moon. So the ones you see here are similar to, but not quite exact to what we'll be sending to the moon.
All right, and Tom also asked, could you define VBB? It looks like maybe 3 instruments in 3 orthogonal directions.
Yeah, I think that's here. Yeah, so VBB is very broadband. So that is composed of 3 components that are orthogonal. So we have a vertical and then 2 horizontal that are laid out. So each of these is kind of considered like an individual sensor. The 3 of them put together are like an instrument package. So yeah, when we use the term VBB, we mostly refer to the 3 of them together, unless we're talking about the individual sensor.
All right. Matthew Oda says InSight had a single seismometer at a single location. How did they locate the meteor strike on Mars without a 2nd and 3rd seismometer to triangulate the location?
Well, so InSight was a single station. It did have 2 instruments on it. So it also had a short period, it also had a BB. So even though it was a single station, it had a total of 6 components. So it had, well, actually it was set up, I don't know if you can see me from here, set up like this. So when you have a single station, the way that you can locate an event is you look at time differences between like the P and the S waves. So if you've heard about like, oh, when you have thunder and lightning, you can figure out how far the lightning is by the time between the lightning strike and when you hear the thunder. Same sort of thing. You can, you see the P wave, you see the S wave, the time between those can tell you how far away an event is. So I can figure out, you know, your, oh God, I can't estimate this, 15 feet? Sure. But in order to figure out if you are this direction from me versus that direction from me, you use your 3 components. So the seismic waves, when they, I think I might have a good example of this. Do I know it's the other way? When they travel along different paths. Yes. Okay. So you have vertical, radial, and transverse. So you can compare the amplitudes from those 3 orthogonal directions to figure out which way it's coming from. So you can figure out if, you know, if my sensor is oriented this way and one of the waves is really strong this way and not strong this way, you can figure out, okay, it came from that direction versus that direction. So that's essentially how we can locate things even with only one station.
Okay, and then Matthew just had a couple of comments, and then we'll turn it over to social media. He said China's space program is run by its military, so that's probably why there's some resistance and cooperation. The Chinese rover landed at Utopia Planitia. JAXA signed the Artemis Accords, and France built InSight seismometer.
Well, no, France built the broadband instrument. The short period was built by Imperial College.
Okay. I do have one more comment from Tom O'Keefe. You mentioned P waves. I experienced 2 separate fracking earthquakes a few years back. When living in Texas during the fracking in the Barnett Shale, magnitude about 2 something, about 15 to 20 miles away. The first I felt an up and down motion, so probably an S wave. The other, it felt like a giant's hand smacked the side of my house with his palm. So I'm thinking it was a P wave. Fortunately, minimal damage, just a few cracks in the drywall in the direction of the epicenter.
So up and down is actually probably a P wave. So you can feel them depending on how close you are. Cracks in your drywall does not sound minor. So might want to have someone look at that. Not a contractor. But yeah, there have been a lot of reports in Texas and Oklahoma of, these events causing similar, again, does not sound minor. I consider, so actually, if you ever do feel an earthquake, the USGS has this great page called Did You Feel It? And you go on, you say like roughly where you're located. It's up to you how specific you want to be. And you basically say like, did you feel it or not? And then it asks like follow-up questions. So it can say like, how strong was the shaking? Like gentle, light, violent. And then we'll ask you things like, were you sitting? Were you standing? Were you lying in bed? Did it wake you up? Did picture frames move? Did chandeliers or things shake? Did things fall off the wall? Did cracks develop in your wall, which is, again, more towards the severe side of the scale. You know, how much damage was done. So it's actually quite useful because we can see, you know, how does damage propagate depending on how far you are from earthquakes and things like that. So if you ever do feel an earthquake, please check out that site and submit a report.
Harry for social media.
Yeah, Stephanie on Facebook asks, what is the core of the moon made of?
Iron, mostly. Iron, mostly. Most planetary cores do tend to be made up of some combination of iron and then with some lighter elements mixed in as well. Like the Martian core actually has quite a bit of oxygen and sulfur in there. So yeah, it's not cheese, unfortunately. Would love a good brie.
Okay, I think that was our last question. So we have covered all of that. Thank you so much for coming tonight and being with us.
Thank you.
We really enjoyed your presentation a lot, and you have to realize that you now have a new obligation. And that is that we expect, once you present to us and you're still collecting data, that you will come back again sometime later and update us on the data you have.
Hopefully it's many years because we're going to be operating for so long. But yes, we do hope to continue doing these lectures with the Artemis program. And yeah, hopefully we'll have more data for you soon.
Oh, super. That would be great. Just let us know.
Absolutely.
You know.
Oh, you'll hear about it.
Okay.
You will hear about it. Yeah. I'm surprised you didn't hear the screaming when we got selected.
Okay. Wonderful. Well, thank you so much for
Thank you.
coming tonight. We really appreciate all of your efforts.
Thank you for having me.
Yes, we enjoyed it a lot. Thank you. And we are, if we sometimes go out to dinner after the meeting, and if we go tonight, we'll talk about that in a little bit, and you're very welcome to go with us. We would love that.
Thank you.
Okay, so now the next thing on our agenda is our planet report. Dr. Kurkashka, also from the Lunar and Planetary Lab, is here to give our monthly planet report.
We finally have all the bright planets in the evening sky, or at least before midnight. And the planet closest to the sun is Mercury. That's visible almost all month up till the November 25th. And it's not very high, so you have to look close to the horizon during twilight around 6 p.m. And then it's just faintly visible. 20 degrees further left and higher up is Venus. And finally, Venus is really getting much higher and more obvious for the last several months. It has just been pretty low at the horizon during twilight, but now it sets around 8 p.m. It's long dark by that time. So it's getting really very bright, obvious. And then in up almost perfectly situated is Saturn. It transits right now around 8 p.m., 50 degrees high. So it's a really nice object in a telescope. Especially now, the rings have opened a little bit up. They were around 3 degrees in spring or so. And now they are 5.4 degrees open. And that's the maximum that it's getting open now, because from now on till next spring, they close completely. And then we'll be 15 years on the other side of the rings. So it should be interesting over the next several months to see how the rings get thinner and thinner, and they become a really thin line in spring. Then Jupiter is just rising before 8 p.m. when Saturn transits, and it's getting towards opposition in December. It's already magnitude minus 2.8, so it's kind of bright enough to cast shadows if they are really the dark side, and look for it. And in the constellation Taurus, Taurus is the northernmost constellation of the ecliptic. So it means it transits 80 degrees high in the early morning. And then the last one of the 5 bright planets to rise, it's Mars. It's rising around 10 p.m. So you have to stay up a little longer for it. But this month it's getting brighter than magnitude 0. So brighter than all the other stars except Sirius. And it's getting bigger than 10 arc seconds. That means you really can see details on the surface with small telescopes. So it's the beginning of the opposition period. Worthwhile to observe. The 2 far planets, Uranus and Neptune, are also in the evening sky. They are between Saturn and Jupiter. Neptune is closer to Saturn, and Uranus closer to Jupiter. Uranus is actually just 6 degrees south of the Seven Sisters. So if you have binoculars, You just look 6 degrees south of there. It's really easy to find. We have a minor planet that number 15, Eunomia. It's magnitude 8 and it transits 87 degrees high, so that's about as high as it can get in Auriga. And for the moon, it was new moon this morning, and tomorrow it's not far enough from the sun, cannot see it yet. But then on Sunday evening, it will be visible as a really slim present. At that time, it will be close to Mercury, but both very close to the horizon. And then the next day, Monday evening, it's close to Venus, and that's always a nice pairing if those two bright objects are together in the evening sky. The moon then goes further. It will cover Neptune on the 12th of November. That's not very often that the moon covers a planet, but occultation starts at 6:40 p.m. And so it's really easy to observe. Neptune finding among those 100,000 stars of similar magnitude isn't that easy, but finding the moon is easy, and so you can then see Neptune just at the edge. And it takes, I think, about 5 seconds or so for Neptune to disappear because it is a disk and it just takes that long. So Neptune occultation is on the 12th at 6:40 p.m. And then the moon goes further to full moon on the 15th, 16th. And the full moon actually will go across most of the Pleiades stars. So we'll occult them. But I don't think you'll see much of it because the full moon is so bright compared to them that you really need a telescope and then look out right next to the moon. And then by the end of the month, we actually have another new moon. So every 3 years, there's a month with 2 new moons, and that's this month. And you probably have seen the comet that went by pretty close and was a good sight in the evening sky. The comet Tsuchinchan Atlas 2023 A3. And right now it's in Ophiuchus and fading, so I don't think it's visible naked eye anymore, but it's still easy sight in binoculars. And then we'll go in the month towards Aquila and fading more and more, and who knows, maybe in 100,000 years we'll return again. Okay.
Thank you very much. And since this covers a month, then it's kind of hard to remember a month-long series of dates or when things might happen. Dr. Kirkashka publishes his blog report, his report on our website in the blog area each month. So you can always go and refer there for something that, you want to recall later when it's going to happen. So thank you so much, Dr. Kirkashka.